So welcome to our series on gases, and today we're going to look at Boyle's law. Robert Boyle was an Irish chemist in the 17th century, and what he studied was the relationship between pressure and volume. And he did this via the J-tube experiment. What he did was he took a tube in a J shape and it was sealed at one end. He trapped a gas bubble in it and then he filled the tube with mercury. He noticed that as he increased the amount of mercury, he noticed the volume of the gas bubble decrease. So what he said was, as the pressure increased, the volume of the gas decreased. So in a given mass of gas, at a constant temperature, the volume varies inversely with the pressure. So if you double the pressure, you're going to half the volume. So anyone who has a fish tank and they have one of these apparatus that releases gas into the tank, what you'll notice is when the bubbles are released, the bubbles will actually increase in size as they approach the surface of the water. The reason being, anyone who's ever jumped into the deep end of a pool, you will feel the pressure of the water pushing on you. And the gas bubble feels this too. So when there's a huge amount of pressure pushing, the water pushing on the gas bubble, the volume then of the gas bubble is quite small. As the gas bubble approaches the surface, the pressure of the water pushing on the gas begins to decrease. And as a result then, the gas can begin to spread out and we see an increase in volume of the gas. So if you look at, say, jumping into the depths of the ocean here, and we move, say, from 1 atmosphere down to 5, say going from 0 meters down to 40 meters, and we took a balloon with us that's filled with gas, we would notice that balloon would begin to shrink as we go deeper and deeper into the ocean. However, as we come up towards the surface, then we would notice the reverse happening, that the balloon would start to increase in size. So really what we're looking at is this relationship between pressure and volume. So gas molecules in a container are constantly bouncing off the container walls. The impact transmits force and thus the pressure on the walls. When a gas is compressed to a smaller volume, the molecules don't have as far to travel to hit the wall, and you end up with more frequent collisions. This means more force and therefore more pressure. So again, if we just have a look at pictorially at that, we can see here we have a gas container here, and it's 10 liters is the volume, and there's a pressure of 1 atmosphere. What happens if I double that pressure? I notice that I end up halving the volume. So as the pressure is increased, the volume decreases. So here is a graph representing Boyle's law. And what do we see? So if we pick a point for pressure, so when the pressure is high, the volume is low. If we pick a second set of points, when the pressure is low, the volume is greater, it's high. So there's 2 different points that we've. So we picked our first set of points where we had a high pressure and a low volume. And what we find is there's a constant at which they vary. If I pick the second set of points where I had my low pressure and my high volume, it varied by the same amount. So we call this a proportionality constant, and B giving the symbol for Boyle. So what are we looking at? These 2 subscripts, V1 and V2, V1 and P1, and P2 and V2, they represent any 2 points on the curve. And we notice that they're both equal to KB. So if they're both equal to KB, then we can say that P1V1 is equal to P2V2. So this equation mathematically expresses Boyle's law, as long as the temperature and the mass are held constant. So if you were asked to describe Boyle's law in the exam, what you could say is volume, represented by V, occupied by the gas, is inversely proportional to its pressure, represented by P. So you could say it, or you could write it in a mathematical form and say that V is proportional to 1 over P. So Boyle determined, remember, that the product, so P by V, so the pressure and volume, is a constant, and this is a proportionality constant, KB. And we can say that KB is equal to PV. So you can also say this to represent Boyle's law. So remember, KB has the same values for all pressure volume, provided the amount of gas and the temperature remain constant. So the same equation should be observed for different sets of P's. For gas laws, you're going to have to memorize a number of different laws, and it can be often very difficult to remember which law belongs to which equation. So to help you try and remember, I have this diagram of the lungs, because the lungs represents a pressure-volume relationship. When you breathe in, the lungs expand. Okay, when they expand, the pressure is going to drop. In order to maintain a constant pressure, you're going to need to fill that extra space, and we do that by breathing in. When we breathe out, the lungs contract, so the amount of space decreases. To stop the pressure getting high and to keep the pressure equal, the same, we need to expel that extra gas, and we do that by breathing out. So you're looking at a pressure-volume relationship, so this should help you remember. Let's have a look at some word problems that you might get for Boyle's law. Let's have a look at this first one. A balloon is filled with 93 litres of air at 1.6 atmospheres pressure. If the pressure is changed to 4.5 atmospheres, what is the new volume? A common mistake that students often make is they don't know which pressure-volume pairs to put together. So let's address that issue first. 93 litres at 1.6 atmospheres. Litres my volume, atmospheres my pressure. So 93 at 1.6. This indicates that these two are a pair. So you would have to call them P1V1, or you could call them P2V2. It doesn't matter as long as you recognize they're a pair. For example, 93 litres, which is a volume, and the 4.5 atmospheres is not a pair, because what we're looking at here is a pressure change and the new volume. So the new volume and the pressure change is the second pair. So for this example, I'm going to call the 93 litres and the 1.6 atmosphere pair P1V1, and the 45 atmospheres and the unknown volume P2V2. So I have 1.6 atmospheres, 93 litres is equal to 4.5 atmospheres times V2. Now it's a good idea to write in your units here, and I'll explain why in a moment. The first thing I want to do is transpose this a formula, so I have my unknown on one side and all my knowns on the other side. I look at the relationship between the 4.5 and the V2, and I see they're multiplied by each other. So in order to get rid of it, I'm going to have to divide all the way across by 4.5. In doing so, I end up with 1.6 atmospheres multiplied by 93 litres, all divided by 45 atmospheres is equal to my V2. Now I notice on the bottom line I have an atmosphere, and on the top line I have an atmosphere, so they will cancel each other out, leaving the only unit of measure as litres. So this tells you what your unit of measure has to be. When I put these numbers into the calculator, 1.6 multiplied by 93 divided by 4.5, I get an answer of 33.06 litres. Now you can check that your answer is reasonable. Let's have a look and see how. I have 93 litres and 1.6 atmospheres. I notice the atmosphere, so the pressure increases from 1.6 to 4.5. Therefore, what would I expect to happen to the volume? Would I expect it to increase or decrease? Well, let's remember that when you increase the pressure, you decrease the volume. So I'm going to expect to see a smaller volume than this. I got 33.06 litres. Therefore, that's reasonable. Let's have a look at a second one. A balloon is filled with 13 litres of air at 1 atmosphere pressure. What pressure is needed to change the volume to 40 litres? So again, let's look for our pairing. 13 litres, litres being our volume, at 1 atmosphere being my pressure. So the 13 litres and the 1 atmosphere are a pair. What pressure is needed? So a new pressure and a new volume. To change the volume to 40 litres, they're a second pair. So my P2 and my V2. So my P1 13 and my V1 volume and my P1 pressure 1 goes in for here. So I have 1 atmosphere pressure and 13 litres. is equal to my P2, which is my unknown, and my new volume, which is 40 litres. I want to transpose this equation to get P2 on its own, so my unknowns on one side and all my knowns on the other. The relationship between these two is they're multiplied by, so I need to divide everything across by 40 litres in order to get P2 on its own. When I do this, I have 1 atmosphere multiplied by 13 litres divided by 40 litres is equal to my P2. I have a litres on the bottom and a litres on the top, so they cancel out, indicating that my answer will be given in the remaining unit, which is atmospheres. When I put these numbers into the calculator then, I end up with 0.33 atmospheres. Again, let's check and see if our answer is reasonable. I've 13 litres at 1 atmosphere. Then look, I end up with a new litre, which is 40 litres. So in order for my volume to increase, what has to happen to my pressure? It has to decrease. So has it decreased? Well, I've gone from 1 atmosphere to 0.33 atmospheres. So again, I'm looking at an answer there. Let's try one more. If a gas sample at a constant temperature occupies 110 mils at 0.950 atmospheres, the pressure it will exert when the volume is 210 mils is. Let's have a look and see. So I have my P1V1 is equal to my P2V2. What are my pairs? The 0.95 atmospheres, the 110 mils is equal to my P2, which is what I'm looking to find, and my 210 mils. Now remember, I want to transpose it to get P2 on its own, so I'm going to divide across everything by 210 mils. So my 0.950 multiplied by my 110 mils divided by my 210 mils. The mils cancel each other out, so the units are the same. Remember, you couldn't have litres here and mils here. You must have the same units of measure for volume as well as pressure. So they both have to be atmospheres, they both have to be pascals, for example, they both have to be litres, they both have to be mils. So just make sure the units are the same for volume and for pressure. So these cancel out, indicating that my unit of measure here is going to be in atmospheres. When I plug these numbers into the calculator, I end up with 0.498 atmospheres for my P2. Okay, I've left some here for you to have a go of. What is the pressure needed to compress 680 mils of nitrogen gas at 1.75 atmospheres to a volume of 385 mils? Use your P1V1 is equal to your P2V2. Fill it in and see do you get an answer of 3.09 atmospheres. If you're stuck, the solution is on the next slide. And here's the solution in case anybody is stuck. And one last one for you to try. A container is filled with 129 mils of argon at 1.03 atmospheres of pressure. What volume is needed to change the pressure to 2.58 atmospheres? The answer in this case will be 51.5 mils. Again, if you're stuck, the solution is on the following slide. So have a go at those and see how we get on. In the next lecture then we're going to look at Charles' law.